So, how you guys doing today? Good, perfect. So you gotta have lunch. Some of you don't. Oh, please, after the class, make sure you go eat for lunch. Okay. So I'm gonna move on to the later parts of the chapter 5. Yeah, chapter 5, and then we actually learn about the Hess's law. Okay, Hess's law or rule. You say. So there's a couple of things I just want you to remember. If there's a chemical reactions there. You can have a enthalpy of change. Okay. So if that is maybe A plus B, okay, makes maybe C over here. Maybe your enthalpy change is maybe X. Okay, just X number, some unknown number here. Whenever you have this reaction over here, you can actually multiply the both sides of the chemical reactions. So you can do 2A 2B makes 2C. Okay. In this case, that enthalpy change of that reaction also can be doubled as well. Okay. So make sure this is the first rule I want you to remember for before we're heading into the actual problem of the Hess's law. So just make sure the multiplication is possible for the both sides of the equations and also the enthalpy change. How about we have this one? This was your enthalpy change was X again here. And then I want to do the reverse reaction. Okay, so I'm going to change the direction and opposite directions over there. So now C making A and B now. Okay, so in this case, you just need to multiply that number for enthalpy change of the previous one by -1. So in that way, this will become -X. Okay, whatever the number that was previously, if you change the direction in reverse reaction, you're going to multiply that number by -1. Okay, so second rule. And then whenever you have A plus B makes C, C makes D and E. Okay, in this case, you can actually add them all together. Okay, so when you add these two together, make sure you have the same thing on the left and right. So eventually, if you add them all together, it'll be A plus B plus C makes C plus D and E. Right? There's this part and this part over here, right? So you have it here. But when you combine these two, if you look at the same elements or compounds on the both side, you can eliminate them. Okay, and then when you do combine those, if you have enthalpy change for this reaction is X, and for this enthalpy change is Y, okay, for this one, when you do have this reaction combined together, we'll show you enthalpy change of X plus Y. Okay, this is the third rule. This is what we did on the later part of the chapter 5 on Monday. Okay. Makes sense, right? Just try to remember these 3 rules, so we'll be able to solve some problems over here. Okay, chapter 5. So chapter 6 is about the electronic structure of atoms. So this is the one that we're going to use a lot of electrons. So there's a big involvement of the quantum mechanics. This is kind of tricky sometimes because in a classical physics view, there are certain things we cannot explain in detail. So for one example, Schrödinger's cat is one good example. It's an imaginary, like an ideal lab you can try. So if you have some chamber on the box, you try to keep the cat inside, and then there is like a tube linked to the chamber, and there was some room right next to it, and there's some like a switch. They can be pressed when it has some nuclear reactions. So if it causes the nuclear reactions, there are certain force will press this button, and this toxic gas will be released to the chamber. Then this cat will eventually, unfortunately, die. But this is an imaginary lab anyway, so there's no cat inside. So the key point here is this one. So we separating this one to one chamber to the under the next room, and this reaction may happen, but 50% chance. So if that happens, the point here is that before you open this chamber, you cannot find out if cat is alive or dead. Okay, so this kind of sounds crazy, but in quantum mechanics, you can say your cat is half dead and half alive, which is quite impossible in the classical physics view. It's because of here in this wall is all happening in very, very small microscopic world. So if whenever, so obviously cat cannot be half dead, half alive. It's obviously true. But in the quantum mechanics, you have to think about it as well. This is the only options we have. Okay? So in that way, I'm going to talk about the light. And I'll tell you why this is kind of a sort of a reason why we do this. So the light is the electromagnetic radiation. So meaning you're going to have a one wave going through the space that is oscillation of the electrical field. Okay? And then perpendicular to that wave, electrical wave, you're going to have a magnetic field oscillating as well. So if you have a electromagnetic radiation that makes your light. Okay? So that's the definition of the light. Okay? So obviously, by looking at this definition, that's what we found from the light. We, in the old time, the class were, the physicists or the chemists thought that, oh, maybe light is just a wave, like a wave. Okay? So we can also prove that by this equation here, which is, this is the C stands for the speed of light. This is we call lambda. Lambda is wavelength. Okay. This is a meter. This is the nu. It's a frequency. So frequency simply means how many something happens per certain time. Maybe in here we use a second. So per each second, how many things can be happening? How frequently that happens per second is a frequency. In this, for here, time unit is a second. So that is why your number for the speed of light will be meter per second. So it means how many meters the light can travel per 1 second. That is approximately 3.0 times 10 to 8. So it's really fast. So I think you guys already heard this. The light can travel, I think 7.5 rounds of the Earth, like in 1 second. That's how long that the 7.5 around the Earth. Okay. So anyway, so if that is the funny thing here, following the Einstein theory, this is fixed at certain conditions. So this is the speed of the light in vacuum, like in most of the universe. Certain conditions. Okay? So this will never change if it's happening at the same. So if light going through the water, it will be different. But if it's light going through the vacuum, like most of the universe, this will be quite close to this number always. It's fixed. Okay. So this is important because as we know, this is a like kind of behave like a wave. We can actually get that number by estimating how many waves. So the wavelength here is just simply how long does it take to get the same position. Here, this is one wave, right? And they try to measure the length of the one wave. So that's wavelength, literally. So lambda stands for the wavelength, just the length of the one wave. Okay. But here's the thing: if you have a one wave here, okay, and the frequency will tell you how many waves you can have. Okay. So for example, if I can step twice per second, but my step is about 0.5 meter. Okay. So my step is 0.5 meter, but I can step twice. So I can do twice per second. So my speed will be what? If we multiply these two, will be what? 1 meter per second. So that will determine the speed of light. If you can find out how many waves will be generated along the space per second, if you just multiply these two, that makes the speed of light. Makes sense, right? Okay. So this is the wavelength, and this is the frequency. This will change. Okay. So in usually visible light range, so the light is a kind of big spectrum along with the different wavelengths and different frequency, because this number is fixed. So for example, if you have some light at certain wavelengths, maybe 500 nanometer, 500 nanometer. So once again, 1 nanometer is equal to 1 times 10 to negative 9 meter. Okay, that's great. So this, if you do the unit conversion for this length into meter, which we need to use meter per second for speed, this will become what? So you can do this one. Okay, over here. So this will become what? 5.0 times 10 to negative 7 meter. So now we switch to the meter, okay? And then, as you know, this one times your frequency has to be what? Speed of light, which is 3.8. Okay? So, if you know the wavelength of the light, you can actually find out the number for frequency automatically, because this number is always the same. So what you can do, you can try to divide it by. If you put this one aside, your frequency will be what? 3.0 times 10 to 8 divided by what? 5.0 to negative 7. Okay? So, yeah. Does it make sense? So if we do this one here, this will be what? This is about, so if you do this one, it's 0.6, right? And do you guys remember this actually? This is 10 power by 8 over 10 by negative 7. This will be 10 to 5th. So you just have to minus this one. 8 minus negative 7 is 15. Okay, and then scientific notation, you want to do it one move, so it'll be not 0.6 but 6.0, and you just need to do this one. Okay. You want to let's try the problem here. Okay. So let's say okay, we have a light here at the wavelength is about maybe 300 nanometer. Okay. What might be the frequency? Can you guys do this real quick? So this will be fixed. Okay. So you can assume the speed of light is always 3.0 times 10 to 8 meter per second. But you find that your light is at wavelength 300 nanometer. Okay, and to do this. About 1 or 2 minutes, or we'll do this together. Yeah, this is. Two curves. Oh, I see. This is carbon monoxide. Okay, so let's test this here. So we have 3.0 times 10 to 8. Okay, should be equal to. I'm going to switch this one in the metric. So it'll be 3.0 times 10 to negative 7 meter. Okay, and then it'll be frequency there. So I'm going to put this one on here. Negative 7. So it will become what? 1.0 times 10 to 15th. Okay. Oh, and this is what? Per second. So this is how many waves you're gonna have this long, and that makes this speed. Okay. Okay. Does it make sense? Can I move on? Yeah, and this is kind of a. Yeah, I just want to tell you, I just look at the question again. I copied the equation wrong. Actually, the question was right. I'm sorry. I'll do this again. Anyway, so the next part. So we know the light is in the wave property. It has a very continuous. So wave. If you look at the wave, it has a wave is like what? The continuous. Okay, so but if you have something that is more like particle-like, like a metal-like, okay. If you have something particle metal-like, meaning it's actually discontinuous. So you have a matter here; it always has end. It's not continuous. Wave is continuous, but this is not. Okay, so the one analogy I normally do is the. Do you guys like to dance? Sometimes? I used to when I was young. The wave is like what? You have a, do you know that's called like wave? It's like a wave. So it's continuous, right? The motion is continuous. But there's another dance I learned was popping. Do you know popping? It's like there's a, like this. It's not like a wave. So it's what? As you can see, it's very discontinuous. So that means these two characteristics is very different. Does it make sense? Okay. So if that is the case, it can't be at the same together, right? It cannot be at the same together. But the funny thing was, light also can be like a particle sometimes. We call them photon. Have you guys heard photon before? Photon. Okay. So if that is the case, I can show you the phenomena we find. So this black body radiation. Okay, and then the second one is photoelectric effects. The third one is a line spectrum. Okay, so there's a 3 phenomena we find that light sometimes behave like a particle. This kind of doesn't make any sense, but like I said earlier, this is something we gotta deal with in the quantum mechanics. So anyway, black body radiation is whenever you try to measure the light, that all has a distribution on all different wavelengths, what frequency you can say, but all of a sudden, sorry, black body means this one. Black body radiation means have you ever been to furnace? So when they try to heat up the metal, they become like a liquid phase, right? Then the metal will start glowing, meaning it will show you somewhat the light and certain wavelengths, which is obviously what? In the range of your visible light. Okay, so then it comes out here, and when it comes to the ultraviolet or UV light reason, it just drops almost none. Okay, so here's the problem. If the light really behaves like a wave, and also it depends on the temperature. Obviously, you have a lot of heat energy to make something glow, like in a very high temperature. But it drops down to the near the UV light or the ultraviolet reason. Okay, so this doesn't comply with the wave because there's no wave on here. If that is true, it would be really, if that shows the wave, it will be really bad because every time you do the combustion, you will be shined by UV light a lot, then you'll die. But normally it doesn't happen, obviously. So this is very discontinuous characteristic right here. It's highly obsessed with the visual light range and the height. Anyway, and photoelectric effect is what the Einstein found. The Einstein found this one by shooting the light on the metal. So if you look at the metal on the light, they become very shiny, right? It's because of the photoelectric effect. So it means when you put the light at a certain high frequency, they actually can enough force to push the electron on metal. So it picks the metal. So metal is a kind of weird thing. The metal has the unique bonding to each other. We call it metallic bond. So in metallic bonds, unlike the other organic compounds, the electrons in the metal will actually freely move easily. This is why metal has very high electric conductivity. So when you try to make the flow of the electron, metal will be the best one to do it. Okay. So anyway, there's a lot of electrons just flowing, making a sea of oceans of the electrons in the metal. But the light goes in with a certain high frequency, they can make this electron pop out. Okay, so we call this photo. Photo means like a photon that later we're gonna discuss as like a light particle. Well, it's not really particle, but photoelectric effects is what it is. Okay, so this is indeed also a good example of what when the light doesn't behave like a wave. Okay, and the line spectra simply means each different element has a certain light coming out from there when they release the electron down to the lower energy level, and that only happens at a certain wavelength. So we can actually make certain wavelength, which is like a blue or light or purple or some of the outside of the visual range, they can be catched by certain different elements. When we try to collect the spectrum from the light, but it's not continuous, but it has some line there between, it's black. So there's a certain light coming out from the certain elements, but only very specific numbers of wavelength, which also doesn't much make sense on the wave-like property. Okay, does it make sense? Does it make sense? Right. So so eventually, what they're really trying to say is the light is actually have two. So it has a dual characteristic. So it has also the wave-like property, but also like particle-like property here. So they have very dual nature of the light. When it comes to the energy, we're gonna do this one. Okay. This is a Planck constant. And this is the frequency we already saw in here. And this is energy of 1 photon. Okay. Yes. So this is later. I'm going to explain more, but this means there are going to be multiplication of the Planck constant frequency, but not in between. So this is a good example of what the literally photon, the discontinuous nature of the light that can be quantified in energy unit. So we call this quantized energy pocket. So we'll do it by these equations. Maybe not today, but on Friday. Okay. So we'll do this on Friday. So let's have an extra credit. Okay. All right. So